Hey, welcome back to Mama Physics. This is question 8 from your interference worksheet. This one is probably more challenging, more things to consider. So let's dive in. Many car exhaust systems use destructive interference to reduce engine noise emitted to the outside. As a simple model, you can simply have two exhaust pipes coming out of the engine of different lengths. For a 6-cylinder engine operating at 2000 RPM, the strongest engine noise will be around 100 Hz. The speed of sound is 343 meters per second, assuming for this environment. To remove the engine noise at 100 Hz, how much longer should you make pipe 2? So here we have the engine. It's going to emit some sound. It will go through pipe 1 and pipe 2 at the same time. When it exits pipe 1 and pipe 2, hopefully there will be no sound left because it's supposed to use destructive interference, meaning that the second wave, sound wave, going through pipe 2 has to go through probably by half number of wavelengths in order to cancel out the wave coming out of pipe 1. Okay, so first of all, notice that we have frequency instead of wavelength. So we need to convert that to wavelength first. We know from the wave equation V is equal to frequency times lambda, so that lambda is our speed over our frequency, 343 meters per second divided by 100. Hertz is going to give us 3.43 meters for our wavelength. So we want pipe 2 to be a bit longer, and this piece that's longer will be our path difference between the wave traveling through pipe 1 versus pipe 2. We want destructive interference, so that the path difference has to be half number of wavelengths. Now, because we're making a car, we don't want to spend a lot of resources on building pipes and just to reduce space. We probably want the least amount of distance as possible for pipe 2. And the least number would give us half number of wavelength difference. Because if you want more wavelength difference, you have to make the pipe even longer. That just does not make sense. So the path difference is going to be equal to half of a wavelength to reduce pipe usage. And that's going to be half of 3.43 meters. And putting that into our calculator, that is going to be about 1.7 meters, which is really long, but unfortunately necessary. Okay, so that's the answer to question A, which is 1.7 meters. And I guess, how many sig figs? We'll just say about 2 sig figs. This is 1.715, by the way, so roughly 1.7. Probably I should do 3, but 100 is 1 sig fig. Anyways, next one. With this design, what other frequencies of noise would also be reduced? Oh, interesting. Okay, so I'm going to do question B down here because I'll need a bit more space. Well then, with this design. Now, imagine that we have to design the second pipe, in which the path difference will be also 1.7 meters, meaning that it's fixed. This extra distance for path 2 for the second pipe will be 1.7 meters. We need to find out other frequencies. So the first one, what we did was we did 1/2 of whatever wavelength there, but we want to see whether or not if we just changed up the number of wavelengths. So for example, we want to find a combination of M. So remember, for destructive interference, we need this one, 1/2 wavelengths, and M is just an order. We pretty much want to change this up a bit. So what happened in the last one is when we had a wavelength of 3.43 meters, M had to be 0 for this to work. So if I make M increase, if I increase M, so that the path difference wouldn't be half a wavelength, it would be 1.5 wavelength, 2.5, 3.5, 4.5 wavelengths, then my wavelength would decrease, meaning I am going to get a different frequency of sound that I can also make destructive interference with as well. So basically for B, for the other frequencies, what we have to do is just vary m. Let's say m is equal to 1, m is equal to 2, m is equal to 3. So we can kind of just plug in some m's and see what we get for lambda. And remember, when we get a lambda, to find a frequency, we have to use the wave equation and the speed of sound to figure out the frequency. So let's do it for m is equal to 1. So we get 1.7 meters is equal to 1.5 lambda. Okay, so we take 1.7 and we divide it by 1.5. We get a lambda equals to 1.1333 repeated, and we're going to convert that to a frequency by frequency is equal to velocity speed of the sound divided by lambda, which is 343 over 1.13 repeated. And that's just from what we did above, but exactly the opposite. We get 302 hertz, or 303 hertz. Okay, I probably should round it to 300, but I'm just trying to convey what this question is doing. Oh, I should probably do a different color. Okay, so for number 2, let's say m is equal to 2. If I run out of space, I'll just do two examples just to show you what I mean. In this one, we'll have 1.7 meters, which is the extra amount of pipe and the path difference. This is going to be 2.5 wavelengths for m is equal to 2. So to find the wavelength, I take 1.7 and I divide it by 2.5. I'm going to get wavelength is equal to 0.68 meters. For the frequency, that's going to be the wave speed, 343, divided by 0.68 meters, and that's going to give us 504 hertz. 504 hertz. Okay, so notice it will continue, and these are all the different sound frequencies that will be reduced, will experience destructive interference. Okay, next one we have C. Okay, we have C. Let's do blue instead. Sorry, I'm not going to do 3. That's just the same idea. Now that you kind of get the idea how to do question B. Question C, with this design, what frequencies of noise will be amplified? So in this case, you're going to look for constructive interference. For constructive interference, the path difference of 1.7 meters is going to not equal to the number of half wavelengths. It will be equal to the number of full wavelengths. So m lambda. Okay, and bonus is something else. Okay, so in this case, again, we are going to look at the values of m that potentially are going to give us constructive interference, and using that we will see what we get for lambda. So I'm going to try for m equals to 0. Actually, that doesn't make sense because that's just no path difference. M is equal to 1, full wavelength. M is equal to 2, and we'll start with those. So for m is equal to 1, we are going to get 1.7 meters equals to 1 times lambda. And hey, that's just lambda. And okay, so lambda is 1.7 meters. Great. So the frequency is going to be our speed divided by our lambda, 343 meters per second, divided by 1.7 meters. And this is going to give us 202 hertz. So sound waves of 202 hertz will be amplified. Let's try what happens for m equals to 2. We'll have 1.7 meters equals to 2 times lambda, and which means I take 1.7 divided by 2. I am going to get, oh, not that big. Okay, so I'm going to get lambda is equal to 0.85 meters. So if I try to find the frequency, this is 343, oopsies, divided by 0.85. And that's going to give me, okay, 404 hertz. 404 hertz. So 404 hertz will get amplified. And I can keep doing this for m equals to 3. I just have to change this number to a 3, to a 4, to a 5, etc. to find my wavelength. I use a wave equation to find my frequency to finish up this question. Okay, phew, next up, bonus. Ooh, yay, bonus. Having extra pipe is expensive and takes up a lot of space. Instead, most standard mufflers include a resonator chamber. A simple example is shown below. That is part of the, okay, so what does it do? It's a standard muffler that includes this chamber that has part of the wave reflect back and forth to interfere with the part that goes straight through. How long would you make this resonator chamber to reduce noise at 100 hertz? Recall that sound waves would pick up a phase shift of pi at each reflection, as the casting of the resonator represents a hard interface. You can treat this problem as 1D. Okay, so what that means is the wave is going to go bounce back and forth, and it's going to bounce back and forth in a straight line, and which then it will interfere with itself when it goes out the chamber on the other side. Okay, so it's going to bounce back once. If we take a look, it bounces here and it bounces the other side and it comes back out. Okay, so how long would you make this resonator chamber? Okay, whew, what a question. Question bonus. Okay, now the path difference for the second wave is going to be, well, let's take a look. For the first wave, it's just going to go through the chamber. So it will travel a distance of L. The second wave will travel the distance of L, comes back again, and then goes back out the other side. So it's going to travel 2 times L compared to wave 1. So the path difference here is going to be 2 times L. Okay, so we need to figure that out first. We also want destructive interference. So we just got to be careful here, because if I have a wave that comes out of here and reflects back, it's going to undergo a phase shift of a pi. But it's going to reflect off the back end, which then it will also undergo another phase shift. Because it goes through 2 half phase shift, by the time that the wave comes back out again, it's going to be exactly in phase with wave 1. Because it went through 2 phase shifts, it will be in the same phase as wave 1. Okay, so we're going to treat this as in phase. They're going to be in phase after all of those, after 2 reflections. Okay, so because of that, we are going to need to, okay, because of that, we're going to look at a constructive interference. Oh, sorry, we're going to look at destructive interference, in which, again, we're going to get m plus 1/2 times lambda, okay, to get destructive interference. Okay, because remember, we want to cancel out this noise. We don't want our car to be so loud. Okay, so we want to also make L as low as possible, because we don't want a resonator chamber to take up so much space. So what is this question? Okay, so again, the lambda here that we use is 3.43, because again, we're looking at frequency of 100 hertz, meaning that lambda in this case was 3.43 meters after using the wave equation to find lambda. So lambda is fixed. We're trying to find L, and we're trying to see what value of m to use. So if we want to make L as low as possible, we need to make m as low as possible as well. So m could be 1, it could be 2, but it could also be 0. If m is 0, then it goes out of this equation. It just becomes 0. Meaning we're going to be left with 2 times L is equal to 1/2 of our wavelength, which is 3.43 meters. And to find the L, all we have to do now is to multiply both sides by 2. So this cancels out. And we're just left with L is equal to, hey, take a look. If, oh, my bad. Did some stupid math here. Okay, we need to get rid of 2 in the L, so we're going to have to divide both sides by 2. My bad. I'm just getting ahead of myself. Okay, divide this side by 2, divide this other side by 2 as well. Bam, bam. We're going to get 3.43 divided by 4. So 3.43 divided by 4. Ooh, we're going to get 0.8575 meters. And let's just say this is roughly about 0.86 meters. So this is going to be the length of our chamber. Okay, so there we go. Phew. So remember, 2 phase shifts is going to get your sound wave back in phase with the original, meaning all you have to do is consider an in-phase situation in which a destructive interference will mean you need half wavelength path differences, and to reduce the L we need to make M as small as possible, and which that's going to give us a total of 0.86 meters for the length of your chamber. Phew, alright, what a bonus, eh? So hopefully this question really tests you, really got you thinking. Hopefully you had fun doing this one as much as I did. It was a lot of work, but hope something to learn from. Thank you for watching. Fan Mama Physics signing out.